Hi, this is Dane Quinn from the University of Akron. And for today's video lecture, we'll deal with sort of a post-velocity analysis. So what can you do once you've finally finished that velocity analysis? The position analysis gives us the configuration of the mechanism, and the velocity analysis then gives us a description of how that configuration changes. So once we know that change in configuration, we can really go and determine the velocity at any point. So we'll go through an example today, and here I have a mechanism, and I actually have three different pictures of it. But let me look at this middle picture here. So essentially this mechanism has kind of an L-shaped bracket. We'll call that essentially link 2. That's connected to link 3 and then a slider. So as this slider moves to the left, essentially link 3 rotates up and unfolds. So this might be a mechanism used for a display system that closes and opens, something like that. And the advantage of this L-shaped bracket is that when L3, this folding link, is flat, the L-shaped bracket is also flat, right? So it forms a nice horizontal surface, and then that unfolds, and we can make L3 vertical. So here again is the mechanism, and if theta 2 is equal to 30 degrees, so that's the orientation of what we're calling link 2, and the block is sliding to the left with some constant speed, I'd like to determine the velocity at point P. So here we have another picture of this mechanism, and really I've tried to highlight the slider crank that kind of lies within this. This L-shaped bracket essentially holds A and O2 a fixed distance apart, right? So you can think about that as an imaginary straight link. And then we have L3 here between A and B, and we have a slider that obviously slides back and forth. So this is an offset slider crank that is kind of embedded in this mechanism. But we're interested in the velocity of P. So if I want to know the velocity of P, I have to first determine the position of P. I can describe the position of P with respect to O2 with this vector. So again, it's a vector from O2 to P. But really, in terms of the mechanism, I'm going to move from O2 to C. And then I'm going to move from C to A. And then I will move from A to P. So we'll write the position of P with respect to O2. Again, that's this vector in orange, as the vector from O2 to C plus the vector from C to A plus finally the vector from A to P. Well, at this point, we need to define some directions so that we can describe these individual terms. So we'll go over here. I and J will be horizontal and vertical. And then I will define I2 to be along the direction between C and A. J2 is perpendicular to that. And of course, the angle between there is theta 2, as given in the problem statement. Now, based on this kind of embedded slider crank mechanism, we'll define another frame of reference like so. I3 is going to be directed from A to B, and J3 is perpendicular, and then the clockwise direction, clockwise angle is theta 3. So with these directions, the position of P with respect to O2 is, well, this is H in the J2 direction. H is the length of this short arm. It's also the difference between the ground and the slider action. And then we'll go out L2 in the I2 direction. And then finally, the vector from A to P is actually in the minus I3 direction with a distance d. So that's going to be minus d in the I3 direction. So now, if I knew all these directions, I could just solve for the position, but I don't. In particular, I don't know the direction I3, or equivalently the angle theta 3. So now I have to turn to a kinematic analysis. So let's go over and look at this picture and identify the loop closure equation. Right? So that's going to be really the vector from O2 to A plus the vector from A to B is equal to the vector from O2 to B. Now, these orange vectors are not the most natural way of describing these terms. In particular, to go from O2 to A, I'll again go through this point C, right? Because we were given this distance is H and this distance is L2. Likewise, because we know the slider moves in the I direction, right, we'll go over by some distance in the I direction and then up a distance H in the J direction. So as part of that, we need to know the displacement of the slider, right? So that's going to be x in the horizontal direction. And of course, the vertical displacement is a constant h. So now, the loop closure equation can be written as the position of A with respect to O2 plus the position of B with respect to A is equal to the position of B with respect to O2. But in terms of these directions and components that we've identified, that's going to be H in the J2 direction plus L2 in the I2 direction equals X in the I direction plus H in the J direction. And I'll point out that this term, H in the J2 direction, is not the same as H in the J direction. Same magnitude, but different directions. So finally, let me look at this constant speed. That was part of the problem statement, right? So the problem statement says that the velocity of the block is minus v in the I direction, right? That's constant speed. To the left is minus I. So here, that's also going to be the change in position. So I want to relate this v to these variables. So here the position of B with respect to O2 is x in the I direction plus h in the j direction. So when I take this derivative, this simply becomes x dot in the I direction. So now comparing this given part of the problem statement with the velocity of B in terms of the coordinates that we defined, we find that x dot is equal to minus v. X dot equals minus v is our known velocity condition, while for the configuration, the known condition is theta 2 is equal to 30 degrees. Right? So I want to know what's going on at P when this link is inclined at an angle of 30 degrees and this block is moving to the left at 20 millimeters per second. Now, this problem asks for velocity of P. And again, P is here at the end of this bar. So before we really get into it, let's figure out how we would represent the velocity of P once we know everything. Again, this is the position of P with respect to O2, and it's given by this orange vector, and we're going to write that in terms of link 2 and then link 3. If we want to calculate the velocity of P, we write that as the derivative of the position of P. Right? So that's going to be the derivative of r of P with respect to O, which again, in terms of link 2 and link 3 is h in the J2 direction plus L2 in the I2 direction. That's link 2, minus d in the I3 direction. Using the product rule here, h is constant, so this first term, the change is only due to the change in the direction of J2. Likewise, the second term, L2 is constant, so it's only due to the change in I2. And then finally, we have a term that looks like the derivative of I3 with respect to time. When we talked about vector derivatives in our previous video lecture, we basically figured out how to write these changes. And what we saw was that the change in a direction is the angular velocity, so in this case the angular velocity of frame 2, which is I2J2, cross the direction itself. Likewise, for I2, it's omega 2 cross I2. And then finally, it's the angular velocity of frame 3 cross I3. So we still need to determine what these angular velocities are. Well, looking at the I2J2 frame, the angle's theta 2, so this frame of reference spins with angular velocity theta 2 dot in the plus k direction. If we look at I3J3, because theta 3 is defined positive clockwise, if theta 3 dot is increasing, then the angular velocity is actually in the minus k direction. So again, if theta 3 dot is positive, the angular velocity here is in the minus k direction. We'll often just write that as minus theta 3 dot in the k direction. And then taking this and putting it back into this expression for the velocity, we see that the velocity of p is h times theta 2 dot k cross j2, then L2, again, theta 2 dot k cross I2, finally minus d times minus theta 3 dot k cross I3. So we need to evaluate these cross products. Well, the way I remember this is ijk, and then actually I'll write another I and a j. And if I cross going this way, it's positive. And if I cross going from right to left, it's negative. So here, k cross j is minus I. So this first term becomes minus h theta 2 dot in the I2 direction. K cross I is theta 2 dot in the plus j2 direction. And then k cross I3, again, is j3. And these two negative signs cancel out, so we have plus d times theta 3 dot in the j3 direction. So if I knew everything, I would be able to determine the velocity. Well, let's see what we know and what we don't know. We don't know theta 2 dot. The problem statement tells us v, right, the speed of the block b, but it doesn't give us the angular velocity of this link, right? So theta 2 dot is unknown. Likewise, theta 3 dot is also unknown. Finally, we know theta 2 because the problem statement had said that this angle is 30 degrees, but I don't know what theta 3 is. So in order to determine the velocity, I need to do a position analysis to determine theta 3, and then a velocity analysis to find out both theta 2 dot and theta 3 dot. And this is kind of the way it goes. If we want to do these velocity problems, right, we have to solve for the position, right? So solve for the configuration, right? And in particular, in this case, these directions. So we'll solve for the configuration with a position analysis. And then we'll solve for the velocity variables. In this case, it's theta 2 dot and theta 3 dot with a velocity analysis. So once we do these, we'll have enough information to go back and determine the velocity of p. So position analysis is first. Well, here is the loop closure equation, again, that we've written out. It's h in the j2 direction, L2 in the I2 direction, plus L3 in the I3 direction is x, and x here is unknown. Theta 3 is unknown. Theta 2 is known, but it's x in the I direction plus a constant h in the j direction. I'd like to find theta 3. So we want to eliminate the other unknown, which in this case is x. So let's write out the loop closure equation again. hj2, L2i2, L3i3 equals x in the I direction plus h in the j direction. And we need to eliminate this term xi. Well, x is an unknown magnitude, so we'll dot this with the perpendicular direction, which in this case is just j. So, working through all this, and again, here are the directions. You can pause this and work these out, I2, J2, and I3, J3 in terms of I and J. I've just rewritten them here for a little bit of convenience. So J dot J2 is cosine of theta 2, and J dot I2 is sine of theta 2. And then we get minus L3 sine of theta 3 equals, well, I dot j is 0, j dot j is 1, so this equals h. And so we can solve, right? It's relatively straightforward to solve for theta 3. In particular, sine of theta 3 here is h cosine plus L2 sine minus h, all divided by L3. And here, these lengths were given in the problem statement, as well as the angle theta 2. So we can work this out and find that sine theta 3 is 0.717. As a result, we find that theta 3 is 45.77 degrees for this configuration. Now, if I want to use the loop closure equation to solve for x, I can do that. In particular, going back and let's just look at the I direction. Right? This is the easiest way of doing this. Right? So in the I direction, we have minus h sine of theta 2 plus L2 cosine of theta 2 plus L3 cosine of theta 3 equals x. So x is 93.6 millimeters, again, in this configuration. So now we can go forward and solve for the velocity variables. So that would be theta 2 dot and theta 3 dot, because at this point we have determined the configuration. This is not part of the problem, but just for completeness, the position of P in this configuration is, well, remember it was h in the j2 direction plus L2 I2 minus d in the I3 direction. So if I use, again, these directions and write this in terms of I and j, L2 cosine minus h sine theta 2 minus d cosine of theta 3 in the I direction. And then in the j direction, I get L2 sine of theta 2 plus h cosine of theta 2, and then d sine of theta 3. Again, using all of the known lengths and angles for this problem, the position of P can be found to be 15.1 millimeters in the I direction plus 93.1 millimeters in the J direction. So again, going from O2 up to P. So now at this point, we turn to the velocity analysis. We'll take the loop closure equation, evaluate the change, and solve for the velocity variables. Recall that the angular velocities of I2, J2 and I3 and J3 are defined like this. And the loop closure equation was h in the J2 direction plus L2 in the I2 direction plus L3 in the I3 direction equals x in the I direction plus h in the J direction. So now, to develop the velocity equations, we take the derivative of this. So each term, we again evaluate the change. So let's look at these one at a time. Again, h is fixed. All these lengths, with the exception of x, are fixed. So this first piece becomes h times omega 2 cross J2 plus L2 omega 2 cross I2 plus L3 omega 3 cross I3 equals, now x changes but I is fixed. So this is just x dot in the I direction. And then h in the J direction is a constant vector, so its derivative is equal to 0. So here we'll use these angular velocities and we'll evaluate these cross products. So this first term, theta 2 dot k cross j, is minus I. So that becomes minus h theta 2 dot in the I2 direction. K cross I2 is J2. So we get plus L2 theta 2 dot in the J2 direction. Here we have minus theta 3 dot k cross I. So that's minus L3 theta 3 dot in the J3 direction equals x dot in the I direction. So these are our velocity equations, right? This is a vector equation. It's got two scalar components. And here, let's start off and solve for theta 2 dot, right? So that means that we want to eliminate theta 3 dot. These directions are all known because we just completed a position analysis. So all these unknown velocity variables appear in the magnitudes. So that implies that in order to eliminate theta 3 dot, I'll dot with I3. Right, so we'll say I3 dot, and then this vector again is minus h theta 2 dot in the I2 direction, L2 theta 2 dot J2. So we'll express this again. And here are the directions again. So when I work this out, I get minus h theta 2 dot and I2 dot I3, cosine of theta 2, cosine of theta 3, minus sine of theta 2, sine of theta 3. Right, so if you want to pause this and work it out for yourself, the next term is L2 theta 2 dot I3 dot J2. So that becomes minus sine of theta 2 cosine of theta 3 minus cosine of theta 2 sine of theta 3. I3 dot J3 is equal to 0. So then we're simply left on the right-hand side with x dot times I dot I3, just cosine of theta 3. So here we can solve this for theta 2 dot. And we get the following. I'm going to make use of some angle addition formulas. This is cosine of theta 2 plus theta 3. This term is minus sine of theta 2 plus theta 3. All right, so this reduces to cosine of theta 3 times minus h cosine of theta 2 plus theta 3 minus L2 of sine of theta 2 plus theta 3 times x dot. Well, remember that x dot was given in the problem statement, right? So x dot is minus v. So when I take all of this, substitute in these angles that I found, the lengths that I know, again, we have minus v here, we have a minus sign that I could factor out on the bottom. We end up finding that theta 2 dot is 0.184 radians per second. So by eliminating theta 3 dot from this equation, we're able to solve for theta 2 dot. Okay, but we also need theta 3 dot, right? So let's go back and do that. Well, I could go and use, say, a component in the ij direction to solve for theta 3 dot now that I know theta 2 dot, but I'm going to go through and do this directly, right? So let's eliminate theta 2 dot. And really the reason that I want to do this is because it's a little bit different. If we go back and look at the velocity equations, theta 2 dot appeared in two different terms. So I'm going to rewrite those velocity equations. I'm going to factor out the theta 2 dot. It's going to be minus h in the I2 direction plus L2 in the J2 direction minus L3 theta 3 dot in the J3 direction equals x dot in the I direction. Again, I'm just rewriting the velocity equations that we found previously. But again, it's not entirely clear what we should do to get rid of theta 2 dot. Well, actually, we just dot this with something that's perpendicular to these two pieces. The easiest thing is to note that L2I2 plus h in the J2 direction is perpendicular to minus h in the I2 plus L2 in the J2, right? So essentially, I'm just finding a direction that's perpendicular to the theta 2 dot terms. So this is a little bit more work because now I have two things that I have to dot. But again, it gets rid of this theta 2 dot term because L2, H2, well, minus L2, H2, and then plus HL2 is equal to 0. So now I just have to take this dot product with these last two terms, and we get minus L2, L3, theta 3 dot, and here this is I2 dot J3, right, this term, and then minus H L3 theta 3 dot J2 dot J3 equals x dot L2 I dot I2 and then plus h x dot I dot J2. So we can calculate all of these dot products. And we end up with the following. Theta 3 dot times, well, minus L2, L3, I2 dot J3. Turns out that that's sine of theta 2 plus theta 3. So here, maybe if you want to pause the video and work this out on your own, J2 dot J3 is cosine of theta 2 plus theta 3. And this equals then x dot times L2 cosine minus h sine. So with this, I can actually go and solve for theta 3 dot. Again, x dot here is minus v. All of these angles are known. And so this reduces to theta 3 dot is equal to, well, in the denominator we have L2, L3, sine of theta 2 plus theta 3, HL3 cosine theta 2 plus theta 3. In the numerator, L2 cosine theta 2 minus h sine of theta 2, all of this times v. And so when I work this out, we get 0.31 radians per second for theta 3 dot. Now, again, we could use the component in the j direction. If I did that, we'd get the same thing. So in the j direction, we would find that theta 2 dot times minus h sine of theta 2 plus L2 cosine minus L3 theta 3 dot times cosine equals 0. And so once again, I would find that theta 3 dot, by solving this, is equal to 0.310 because theta 2 dot we found was 0.184 radians per second. Again, I'll be honest, this is much easier, but I did want to show you an example where the terms that you're eliminating contain more than one direction, right? So like we have here, it just requires that you figure out what the perpendicular direction is. But either way, we end up with the same answer. Okay, so we're almost done because let's go back and look at those velocity equations for the velocity of p. We needed theta 2 dot. Well, I have that. Theta 2 is 30 degrees. We needed theta 3 dot. Got that. We needed J3. Well, got that too. So we are ready to go and determine the position of P, right? So here was the position of P again. Here are all of these things that we calculated, right? So as a result, the velocity of P, and I'll write this in the I and J direction. In the I direction, again, using these relationships that we have here, minus h theta 2 dot cosine minus L2 theta 2 dot sine theta 2 plus d theta 3 dot sine of theta 3 in the I direction. And then in the j direction, we have minus h theta 2 dot sine. Again, we're just taking these direction vectors, putting them into this expression for the velocity of P, collecting terms, L2 theta 2 dot cosine plus d theta 3 dot cosine theta 3 in the j direction. So when I take all of this, plug it into here, the final answer is 4.99 millimeters per second in the I direction, 24.32 millimeters per second in the j direction. Using our configuration and velocity analysis, we see that the position and velocity of any point can be determined. But we can only do this once the position and velocity analysis are complete. So this position and velocity analysis, they provide a lot of information, but they're really not the be-all, end-all of our kinematic analysis. What we hope is that we can use that information to then go and say useful things about how the mechanism moves. So this has been a pretty exhaustive example, but this is kinematic analysis. So I hope you enjoyed it. I will talk to you again soon. Take care. Bye.